Hey folks, Mrs. White here. Today's a day where things start to overlap again. So today's lesson is actually going to cover bits and pieces of two sections, and that's going to start and introduce and then talk about the properties of logarithms and what logarithms are overlap kind of with two things that we've already learned this year. So we'll talk a little bit about that. I'm going to warn you right now, this is going to be a long video. I am going to try to cover two lessons today, and I know that that can be stressful, but what I want to let you know is that your assignment tied to this is going to be reasonably quick and easy, okay? It's going to be two Khan Academy assignments, so it's a maximum of 8-ish problems. Hopefully they will go reasonably quick, and your goal is to get a 75 or better, okay? So what I would probably encourage you to do is set aside right now, if you can, 1 hour and 15 minutes. Or give yourself about 35-40 minutes to watch half this video, do the practice, and then come back and watch the other half of the video maybe tomorrow instead of watching everything and then doing the Khan Academies later. I'd probably watch this section, do this Khan Academy, watch this section, do this Khan Academy, and then be totally done for math, okay? I know it's kind of tricky, but in order for us to be able to finish this chapter, I took out section 6.3, I took out section 6.5, and I'm hoping that what I've left today will help kind of build a foundation for how logarithms are related to what we've done already and how we can start computing with them, okay? So hold on tight, go get yourself a nice soda pop, maybe some cookies, okay? And we'll get started. So our sit and begin is going to review a bunch of stuff that we've already covered so far. So I have an exponential graph here. If you look over here, I have solving an exponential function, and then down here I have a word problem. So if you don't really find any benefit in going over these to review right now, you can feel free to watch it on 1.5 or just skip this section and go right to where we start talking about some new stuff. But I thought for some of you, you would benefit from a little bit of review right now. So I notice this is an exponential function because it has a variable in the exponent. I also notice right here the base that's holding up my variable is a number that is greater than 0 but less than 1. So this is going to be an exponential decay function, which means it's going to look something like this, okay? And it's going to have an asymptote. I notice also that there's a -1 on the outside, which means that everything is going to be shifted down 1. So the asymptote that would normally be at 0 here is going to be moved down 1 space, and it's now going to be located here. Now, in order to actually graph my function, I need to make a table. I'm going to do 3 points on this table. I'm going to choose 3 values that give me -1 up top here, one that's going to give me 0 up here, and then one that's going to give me a +1 up here in the exponent. So if I want x plus 3 to equal -1 at -3 minus 3, my x value would have to be -4. If I want to get an exponent here that's equal to 0, I would set this equal to 0, -3 minus 3, and I get x would equal -3. And then lastly, if I want it to equal +1, then I would -3 minus 3, and I'm going to get -2. Okay, so these are going to be my 3 x values that should make it so that I'm able to compute pretty reasonably. So let's start doing that. Let's start by having a -4 here. So -4 plus 3 is -1. Anything to a -1 power, you just kind of take the reciprocal of it. So this is going to become 5. 4 times 5 is 20. 20 minus 1 is 19. Whew, that's big. Okay, I probably should have set up a scale here before I moved that down 1. Let's take a look at our next one. -3. So I'll plug -3 here. -3 plus 3 is 0. Anything to the 0 power is equal to 1. So I have 4 times 1, which is 4, minus 1 is 3. Wow, that went down really quickly, which makes sense, right? It's going to be really steep. It's going to go quickly. It's going to decrease, and then it's going to certainly flatten out. My last number I have here is going to be -2. So let me erase this stuff, and we'll go to orange. If I have a -2 here, -2 plus 3 is 1. 1/5 to the first power is just going to be 1/5. So I'm going to put this over 1. I get 4/5. So I currently have 4/5 minus 1. Well, I can kind of imagine this in my head, right? This is less than 1, and I'm going to minus 1 from it. So I'm actually going to have 1/5 left over, but the negative number is larger, so it's actually going to be a -1/5. So you know what? I feel like I'm going to graph this anyways. I'm going to start by going over -2, and I'm going to go down 1/5 of a box. Okay? Then I'm going to go over, so I'm just starting at the bottom and working my way up. I'm going to go over to -3 right here, and I'm going to go up 3 boxes. And then I'd go over to -1, 2, 3, 4, and up 20 boxes, which would be way the heck up here. Again, this follows, right? This follows my exponential decay function shape pretty closely, right? Really steep and then kind of evening out. So here we go, really steep. And then, oh yeah, this is not easy, evening out. Okay, you can imagine that this like actually hugs it the way that it should. Okay, but it's going to be heck yeah, really steep and then coming down and evening out. Remember, it never hits this asymptote, and this asymptote is at y equals -1. Now, so that was a couple classes ago. We discussed that. Last class, we looked at solving. Okay, how do we go about solving exponential functions? So the big idea here is if you have something raised to an exponent and something else raised to an exponent, we want our bases to look exactly the same. So maybe 36 times 36 is 216. Let me check. Whoa, no, it is not. It's like 1,000 and change. So what I'm going to do is I could check and see, maybe I can put this in a 6, like I can break this into its prime factorization. So 36 is the same thing right now as 6 and 6. So I could write this as 6 squared, which I'm sure a lot of you noticed. But I wonder if this is something like a 6 raised to a certain power. So if I do 216 divided by 6, I get 36. It is, okay? So 216 divided by 6 is 36, and 36 divided by 6 is 6. So this is the same thing as 6 to the third, and this is the same thing as 6 squared. So we didn't have to bring it all the way down to 2s and 3s and 1s, okay, or whatever. We can stop at 6s because now they'll both have the same base. So that means I can rewrite 36 as 6 squared, then raised to the 2x plus 4. And I can write 216 as 6 to the third raised to the x plus 5. And then I'm just going to distribute my exponents through. So 2 times 2 is 4. This is going to become 4x, and 2 times 4 is 8, so 4x plus 8. Then this 3 is going to go to the x and to the 5. It's going to become 3x plus 15. And now, because they have the same bases, I can even cancel out those bases and just have 4x plus 8 equals 3x plus 15. Now I'm going to move everything to the same side, so I'll minus 3x, minus 3x. I'll get an x over here. I'm going to minus 8, and I'm going to get a 7 over here. Ta-da! There's my solution. Okay, so again, we want to have those same bases. Look at what, this is clearly a perfect square. So I was like, I wonder if this is divisible by 6, and it ended up being perfectly a perfect cube of 6. Okay, let's go down to a word problem. And I know word problems are not your favorite, but they tie in a lot to exponential functions, and they actually tie a lot into logarithmic functions. We're not going to tackle any word problems today, but there's a whole section about modeling with logarithms in your book. We're not going to get to it this year, but I'd be happy to put some practice together for those of you that might be interested. But for now, let's just take a look at this one. Ahmed's consulting firm began with 23 clients. So that's an interesting word right there, began with 23. After 7 years, he now has 393, okay? He now has that much. Write an exponential equation describing the firm's growth. So it clearly went up over the past 7 years, okay? So we know it's going to be growth, so we know that our B value, or our growth factor, is going to be bigger than 1. So we do not know our growth factor. We can't just plug these 3 things in and be done. Instead, we need to be thinking in our head, y equals ab to the x. A is our initial amount, B is our growth factor, and X is the amount of time that's going to be passing. So we know a handful of these. We know that it began with 23, which is going to be our A value. We don't know what it's grown by. It doesn't tell us. We know how much we ended with, though. We ended, and Y is always our dependent, right? It's what we end with. That's our resultant, 393. Again, we don't know what it grew by, but we do know our time period was 7 years. So I'm just going to go through and solve this. I'm going to get my B alone and positive. I'm going to divide by 23, and 343. 343 divided by 20. divided by 23 equals 14.91. So 14.91 equals b to the 7th. So I'm going to 7th root. So I'm going to type in my 14.91. Then I'm going to press my square root with the y, and then I'm going to put a 7 right there. And I get 1.471111, or 1134, blah, blah, blah. So I end up getting that b equals, when I 7th root this number, 1.47 approximately. Now 1.47 is not my answer. 1.47 is my growth rate. It's my B. So now I'm going to plug back in the stuff that matters. I don't care what I ended with because I want to be able to calculate it for every year. I do need to know how much it started with, right? That's going to be my A, and that stays the same every time. My growth rate I just calculated is 1.47. And then I don't know how many years. I want to write an equation that's going to figure it out for every year. So now at this point, I could type in 3 here or 10 here or whatever. And then if it follows this exponential trend, I should be able to calculate how many actual clients they have at that given year. Okay? All right. So there's a review of pretty much everything we've covered so far. In our exponential and logarithmic unit, let's start talking about what the heck are logarithms, okay? So some of you maybe have heard of logarithms, or you've seen the word log. Maybe you've seen or heard of a natural log. We're going to be talking about, this is actually our common log, and this is a natural log. We're going to talk about those two special things specifically, but a logarithm in general is the inverse of an exponential. That's why I said that today kind of overlaps with a lot of stuff, because we learned about inverses in chapter 5 and we've been talking about exponentials in chapter 6. So it kind of lends itself to a lot of review from the previous sections. So say we are wanting to figure out what the heck does a logarithm actually look like, right? What does the graph of it look like? We should know something about things that are inverses, right? If we have an exponential function and it starts slow and it increases rapidly, its inverse should be reflected over the line y equals x. So let's just, it's hard to make the exact graph of this, and I couldn't write what we wanted. What I wanted to do is 2 to the x, and I wanted this to be 2 to the y, right? Because to do the inverse, you flip-flop your x and your y. Let's just graph this first. We should be familiar with it, okay? We're going to do a handful of points. Let's do -1, 0, and 1 as our exponents. That way we can kind of get an idea of what this looks like, and then we'll figure out our inverse for it, okay? So if I plug a -1 here, it means change the location. So it's going to become a 1/2. And there's nothing to add or subtract or multiply to it. If I put a 0 in here, anything to the 0 power is 1. And then if I stick a 1 in here, 2 to the 1st power is just 2. So I'm going to graph these up really quick. I only have to go, let's just go out 2 in each direction for now. So I'm going to graph this exponential function, right? It has x as an exponent. I'm going to go over to -1. Maybe we make this one red. Okay. I'm going to go over to -1. I'm going to go up half a box. I'm going to go over to 0. I'm going to go up 1 box. I'm going to go over to 1. I'm going to go up 2 boxes. So you can see here, there's our exponential growth function. It's going to come right down. It's going to hug, if you remember, we end up with an asymptote right here. It is going to hug that x-axis, but never actually hit it. So think back to inverses. We flip-flop our x and our y. Now you're like, oh, we want to get our y alone in positive. Well, that notation is actually where log comes into play. We're not going to worry about that notation right now. I just want to show you the graph, okay? So if we flip-flop x and y, back when we started inverses, we talked about you can just flip-flop your coordinate pairs. So I could have a 1/2 for x, and that would mean that my y is going to be -1. Remember, inverses are just your x and y's flip-flopped. So if I have, oops, that's not what I wanted to do. If I have a 1 that was in my x, I can plug, or in my y, I can plug that in for my x, and I would get out 0. Or really, I could just, maybe I should word this differently. Instead of plugging in for x's, I should just plug in -1, 0, and 1 for y, right? These are the y values that I want, and y is in the exponent, so -1 here would be 2 to the negative 1, which is just the reciprocal. I could take a 0 for my y, plug a 0 in here. 2 to the 0 is going to be 1, so x would be 1. And then lastly, I could plug in a positive 1 for y. 2 to the first is 2, x equals 2. And now I'm ready to plot these points. So I'm going to go over half a box, and I'm going to go down to negative 1. I'm going to go over one box, and I'm going to go up 0. Then I'm going to go over two boxes, and I'm going to go up 1. And if you take a look at this, folks, it seems to kind of look like a square root at first, but it's actually going to continue on. And instead of hugging the x, it is going to hug the y-axis. It's going to have an asymptote right here, which makes sense because if you take a look, folks, here's our line, y equals x, right? A slope of 1 going right through the origin. Boom, 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 boom. You can see that they are reflections of each other over that line. Okay, and that lets us know that they're inverses. So the graph of a normal logarithm is going to have an asymptote at y instead of on x. And it's going to kind of end steeply to the left, going either down, or if it's a reflection, it would be going up. And then it kind of evens out as it goes on. Okay, kind of evens out, slows down a little bit. The curve kind of gets a little bit flatter. And that's where a logarithm comes from. It's the inverse of your exponential function. Now, we have no strategy to get our y out of an exponent right now, to put it in terms of y. And that's where, like I said, the notation for logarithms come into play. So this is right from our text. It's a little tricky at first, but the example's really good. So it says, and again, the wording is tricky, let b and x be positive numbers, and b cannot equal 1. Okay, so our base number here cannot be 1, because 1 to any power, it's not going to end up being a function that works. It has to have a growth factor, or it has to be, a decay factor. If it equals 1, then it's just a line. It's not going to be a logarithm or exponential. So anyways, the logarithm of x with base b is denoted log b of x. Okay, that's how we say it, log base b of x. It is defined as the exponent y that makes the equation by equals x true. Okay, so that's a hot mess right there. But what they're saying is that this and this are the same thing, as long as b is not equal to 1. B can be smaller than 1, b can be bigger than 1, but it can't equal 1 because it would be a line. Okay. So here's another couple important things to remember. B, your base, not only can it not equal 1, but it has to be greater than 0. You cannot have a negative base. Hopefully you're hearing me right now. When we're dealing with logarithms, you cannot have a negative base, okay? And then obviously your base can't equal 1. When x is greater than 1, there's a number y such that we can rewrite it like this, okay? So if we have log base b of x equaling y, we can rewrite it as this log base b is the base, the whatever's on the other side of your equal sign becomes your exponent, and then it's going to equal whatever your of piece is right here. Now that seems really tricky, but if I were you, I just take a quick second. I want you to write this down. I want you to write log base b of x equals y, and then a little arrow, and then b to the yth power equals x. And we're going to practice converting back and forth, okay, between what we call logarithmic form and exponential form. Just like we had radical form and exponential form before, we're going to have logarithmic form and exponential form. So here's a really good example, okay? So if we have log base 3 of 27 and it equals y, we take this, it becomes our base number. You take the equals, that becomes your exponent, and then your of piece is what it equals on the other side here. So log base 3 of 27 equals y is the same thing as 3 to the what power equals 27, and you can actually solve for y here, right? 3 to what power equals 27? Well, 3 to the third power equals 27. So we could say y equals 3 in this form, but that means we can also apply it here. Log base 3 of 27 is y. Again, tricky, tricky, tricky. I understand it. We're going to try to practice it a little bit right below, just changing the forms, okay? So we're going to take each equation and write it in exponential form. So it's currently in log form because it says log. We're going to rewrite it with an exponent. So first things first, you're going to look at your base number, 2. That is the base number that you're going to have. Next, you're going to find your exponent. Your exponent is going to always be the opposite side. 3 equals 8. And in all of these, it's going to work out nicely, right? 2 to the third power is 2 times 2 times 2, and it equals 8. It works, okay? Gets a little bit trickier. Let's look at our next one. We're going to look first, log base 4 of 1 over 256 equals negative 4. Don't worry about the fraction or the negative. You're just going to go right to your base number here. It's going to be the base that holds up your exponent. Your exponent is always the other side of the equal sign. Negative 4 equals 1 over 256. So let's think about this for a second. The negative means put it over 1, right? So if we're thinking, what is 4 to the negative 4? Well, it's the same thing as 1 over 4 to the 4th. And 4 to the 4th is 4 times 4 times 4 times 4, 16 times 16, which happens to be 256. So that's where they get this 1 over 256. They're just giving you the actual answer, okay? So that's how we change it from logarithmic, right? We take our base, we raise it to the power of the other side of the equal sign, and then set it equal to whatever's here, okay? Going from exponential to logarithmic form, we want to do the same thing. You're going to start off with your word log. Then you're going to find your base, right? The number that holds up your exponent. Our base here is 15. Then we're going to go to the other side of the equal sign. That is the number that goes with it. Remember, your exponent is not right next to this, okay? So I go to my other side next, which is going to be my 3375, equals, and then it always equals that last exponent, okay? So remember, 15 to the third equals 375. So it's almost like a circle, right? You got to come full circle. 15 to the third equals 3,375. So give this one a go on your own. All these you can always give a go on your own. Actually, I have 4 examples that you're going to do after this. So let's actually do this one together. My base is 4, so my log base is going to also be 4. Right next to it, I'm going to put my other side of the equal sign, and then an equal sign, and then my 1/2. And that's logarithmic form, okay? Base, exponent, equals. Base, exponent, equals. Base, exponent, equals, okay? You can kind of use that thought every time. So over here I have 4 examples. I want you to take a second and mentally try to solve them, okay? Pause the video, then I'll do it, and we'll talk through it, and then pause the video again, try to do the next one, okay? So let's take a look at this first one. I'm actually not going to have to write anything. If it's in logarithmic form, I'm going to put it in exponential. So I'm going to start here. This is my base of my log, so it's the base number. So it's going to be 4 squared equals 16. 4 squared equals 16. I don't care if the equals is before or after. So you're going to come here. Again, if you need to, pause the video, take a guess, and then come back. 3 to the 6th equals 729, okay? Now, we have to do something different. It's in exponential form, so we need to change it to logarithmic form. Now, this is still the base, so it's going to be the base of our log. So it's going to be log base 4, go to the other side of the equal sign, of 64 equals 3. Log base 4 of 64 equals 3. Okay, that way we can always go back and check it the other way, right? 4 to the third equals 64. Same idea. You do that little kind of half circle it back. So then here we're going to have log base 125 to the 5th equals 1/3. Log base 125 to the of the 5th, or blah, 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 blah. Log base 125 of 5 equals 1/3. Okay, the only way you get better at those is by doing them and doing them and doing them. So to start evaluating logs, it means we're actually going to figure out what the heck does this equal. Okay, if we look at the previous examples we all did, they gave us a log and they told us what it equals already. This isn't an equation, right? I mean, it is an equation because it has an equal sign, but there's no variable to solve for, okay? And so everything worked out perfectly and equally. So here, when they tell us to evaluate some log with some base of some number, okay, they're telling us we need to figure out what exponent can I raise 16 to that's going to give me 4? Okay, so the first step that you want to do here when you're asked to evaluate some sort of log is to rewrite it in exponential form. Okay, now you might be like, well, Mrs. White, I can't rewrite this in exponential form because it doesn't have an equal sign and it doesn't have something over here. Well, put an equal sign, and then we don't know what the power is, okay? That's what we're solving for when we're solving for a logarithm. We're trying to figure out what exponent to do. So since that's our unknown, we're just going to set it equal to x. Now we're ready to do our first step, which is write it in exponential form. We're going to do 16 to the x power equals 4. So 16 to the x power equals 4. Now, right now, you might be utterly confused. Like, I don't know, what power can you do that's going to make it smaller? Maybe you already have an idea of what that power is that's going to make it 4. But this is just an exponential problem, and an exponential problem is what we know how to solve, right? From our begin. So what we need to do, and what we did here, is we need to get the same bases, right? So we're going to go back there and we're going to rewrite them with the same base. Okay, this is just an exponential function, and now we know how to solve that. Okay, so 4 is the same thing as 2 squared, but I know 16 actually is also a perfect square. It's the same thing as 4 squared. And then they'll have the same base. So I could say 16 is the same as 4 squared. So I'm going to raise that to the x equals 4 to the essentially first power. So this is my exponent property. It's going to just become 2x. And then my bases are going to cancel because they're exactly the same. So I'm going to be left with 2x equals 1. Divide 2, I get x equals 1/2. Okay, and hopefully you're like, oh yeah, I totally get that, right? If we have 16 to the 1/2, if you think back to what we did in chapter 5, anything that has a fractional exponent means that it can be rewritten in its radical form. Okay, we take our denominator, that becomes our index, so it's a square root of 16 to the first, or just 16, and the square root of 16 is 4. It totally works out. Okay, so we first rewrote it in exponential form. The second thing we did right here is we made them have the same base. Once you have the same bases in both of them, you just take your exponents and you set it equal to the other exponent. And you cancel out your bases because they're the same. You don't need to worry about it. So really, once you rewrite it in exponential form, this is the same work we did with section 6.2, right? Find the same bases and set exponent equal to the other exponent. So take a second right now, pause the video, and give each of these a go. So in this first one, and I'm going to actually talk you through this because we haven't done a lot together, and then you'll hop on Khan for your first homework piece, which is evaluating logs. We're going to do all 3 steps for this one and all 3 steps for that one. So I'm going to start by writing it in its exponential form. It's going to be 3 to the who knows what power equals 81. Now, hopefully you know something about your 3 to whatever power. You're not going to x root both sides. You can just kind of guess and check this if you wanted to. I know 3 times 3 is 9, and I know 9 times 9 is 81. So 9 times 9 would be 81. So I'm actually going to have to do 3 to the 4th. So I can just do this with mental math. I can know that x is going to equal 4, which you are welcome to do if you can. But if we were to follow this strategy, okay, once I get here, I want to have the same base. So I would currently have 3 to the x equals, now 81, I need it to have bases of 3s. So 3 times 27, 3 times 9, 3 times 3. So I could say 3 to the x is the same thing as 3 to the 1, 2, 3, 4, because that's equal to 81. My bases cancel. I'm left with x equals 4. So either strategy works, okay? If you can do it with mental math, great. If you want to check it, you want to do your factoring, right? Just like we did with normal exponential functions. This one's going to be a little bit trickier because it's got that fraction in there. But let's tackle it anyways, right? We're going to start by rewriting it in its exponential form. So I take my base of my log, okay? Now, you're like, can it be a fraction, Mrs. White? Yes, it can. If we look back, as long as it is greater than 0, but not equal to 1, then we're good. If that is a negative, then we can't do anything with it, okay? So what this is 1/2 to the unknown power should equal 256. Now you might be like, what right now? This is actually a very, very tricky problem. It will probably be trickier than any of the ones you're going to see on Khan Academy. So first thing I notice is that this is a fraction and this is not. Now I can do something to this to make it not a fraction, right? If I could move this 1 in the bottom and this 2 in the top, if I could take the reciprocal of this, then I wouldn't have to worry about it being a fraction, right? Well, if you remember our exponent properties, if this x was negative, it would change those locations. So I'm actually going to rewrite this as 2 to the negative x. That is an equivalent situation. 1/2 to the x and 2 to the negative x are the exact same. So what that means now is I want to take this 256, and because, oops, I shouldn't have drawn a line there. Because this is now a base 2, I don't want to see how many 1/2s go into that. That's crappy. But now that it's a 2, I want to see how many times can 2 fit into it. So if I divide this by 2, I get 125, 26, 27, 28, 128, which is even again. I always am looking for 2's because this is a base 2. So that's going to be 64. 64 cut in half is going to be 32. 32 cut in half, because again it's even, is going to be 16. 16 cut in half is 8. 8 cut in half is 4. 4 cut in half is 2 and 2. So 256 is actually equal to 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8th power. Right? And you guys see hopefully how I got that. Remember, I chose to divide by 2 because that was my base over here. Okay, and I could make this 2 by making it negative. It meant that I applied a negative to the 1, move it below, a negative to the 2, move it above. So now, since those are same bases, I'm left with negative x equals 8. So then positive x would have to equal negative 8. That one was super duper tricky. There is potential for you to see those moving forward, but I'm not trying to mess with you a whole bunch today. I just want you to practice things and start feeling good about it. So right now, there's a link on the classroom, but I really want, if you know your login, just to log into Khan Academy like normal. I've sent you 2 skills. I want you to do this one first, which is evaluate logarithms. Okay, which is exactly what we were just doing. I want you to give those 4 a go. I only want you to do this activity twice. If you end up doing it 2 times and you don't get a 75 or higher, then please stop and attend office hours. Do not just spend an hour doing this problem, okay? This is not the point. It's a long lesson today. We're only halfway through. I want you to just get a little bit of practice, and if you need help, I want you to come see me. So we'll do this one together, okay? So I'm going to look at my base. It's 3. I'm going to raise it to some unknown number. Equals 729. So my first thing is put it in exponential form. Now I need them to have same bases. So 729, I need that to have a base of 3. So I'm going to divide 3 into it. So I'm going to go right to my calculator because honestly, I don't know this by heart, okay? I'm going to go 729 divided by 3, and I get 243. I'm going to do 243 on my calculator divided by 3, and I get 81. And right now I feel good because I know 3 goes into 81 nicely. I'm going to divide that by 3 and get 27. And that by 3, and then my last piece by 3. And then I can see that 729 is actually 3 to the 1, 2, 3, 4, 5, 6, 3 to the 6th power. So I could rewrite that as 3x equals 3 to the 6th. Clearly then, my bases would cancel. X is going to equal 6. So let's check a Rooney. Yay! I got it right. Okay, now I have 3 more to do. Because this is evaluate and this is not the advanced evaluating, I think all of your exponents are going to be reasonably nice. If you want to take a go at ones that could be negative or fractions, then please give a go to this Khan Academy also. I did not assign it. If you do want to give this a go because you feel really good and you want to take on an extra challenge, feel free to do it. If you take a picture of it, and submit it with your homework stuff, then I will give you an extra bonus point on this homework assignment when I put it online. Okay? So right now, pause the video. Maybe this is a good spot for you to get some practice, and then come back and do the second half of the video later if you'd like. All right. So now that we've done some evaluating, I want to talk about the properties of logarithms. And as you can see, there's not a lot of slides left because we're going to actually use a Khan Academy resource link to do some learning about these 3 properties, and then we're going to do 3 solving problems. Okay, so let's talk about these 3 properties. Maybe take a second, write these down in your notes, and then we'll look at kind of the Khan resource. It's not practice, it's actually one of their articles, and I thought it was pretty darn good, so I thought it would help guide our discussion today with some resources, or with some examples in it. So this is from our text first. There's 3 properties we're looking at with logarithms. One of them is called the product property. So, long story short, let's take a look at what this is actually saying. Okay, words are miserable, symbols aren't necessarily great, okay, but it does tell us this. Okay, so if we have a log of 2 things being times together, it's the exact same thing as log base, that same base, of the first piece being multiplied plus the second piece being multiplied. Okay, so we can expand multiplication into an addition of 2 logs with the same bases. That's what that means. So let's say over here we have log base 2 of 5 times 6. That is the exact same thing as log base 2 of 5 plus log base 2 of 6. Okay, and that's a property that will work each and always every time. Our next property is the quotient property. Okay, so quotient we know has to do with division. So if you think about the product property, right, if we multiply them, we can add logs. If you divide them, you can subtract the logs, top minus the bottom. Okay, and that's really what our quotient property is here. It's this idea, and this is probably what I'd put in my notes. Log base x, so your bases have to stay the same, of something divided by something else is just that numerator subtracted by the log of that denominator. Okay, same exact thing. And then lastly, we have the power property of logarithms, which tells you if you have log base something, and then this of piece right here has its own exponent, you can just take that exponent and put it right out front and make it a coefficient. Okay, so that 5 that was a power could also be written as a coefficient here and canceled out there. Okay, so they write it with an M and a P. I don't know why M and P feel so weird to me versus A and B, but this might be what I end up putting in my notes, right? So if we have some log and it has a base of B, and then the of piece is an M with its own exponent, that exponent can be written in front, and then everything else stays the same. That way that piece isn't so tricky. So let's take a look at Khan Academy. It has a couple built-in practices. You are not going to do this part. It's separate from the practice that I have you doing afterwards. So this is just to guide our conversation right now. So if we take a look here, again, this is not your homework piece. This is just to guide our discussion. We have our 3 properties written here. Instead of using A and B, they used M and N. You're welcome to rewrite them in your notes with M and N if you like. But again, the product rule tells us if we're multiplying 2 things in our of, we could expand it, okay, to be an addition problem. If we were given an addition problem, we could condense it to be a multiplication problem. So this goes both ways, right? We could make it larger by expanding it to a plus, or we could make an addition problem smaller by making it a product, okay? They both work both ways. Similarly, our quotient rule has m divided by n, which is the same thing as m minus n, okay? Remembering they have to have the log base b attached to each of them. And then lastly, our power rule has that exponent attached to your of piece as a coefficient there attached to just that log. Like before, your b has to be greater than 0, but not equal to 1. And then here's something a little bit new too. As you're thinking of your m and your n, okay, m and n must be greater than 0 for logarithms to work. Okay, they have to be greater than 0. So we've already done a little bit of an intro to logarithms. If the intro first part was a little tricky, you're welcome to come to this site and just give a click here or look on Khan Academy. Like I said, they have great resources, and I'm not always the best at explaining stuff. I know that. No one can be the best all the time. So please use your resources. They give you a little summary of what we're going to learn in this article. It's a pretty long article. You can see, woo, okay, but this is going to be what we're looking at today. So we're going to learn about all the different properties. So we'll start with the product rule right here. Now this is exactly what they gave us above, and this is exactly what our textbook told us, okay? So the product this property says that a logarithm of a product is the sum of the logs of its factors. So they have to have the same base. And if two things are being multiplied together, we can write them as an addition problem. So if we're asked to expand our logarithms, okay, that would mean we'd take something that looks like a product like this. Okay, this is technically 5 times y, right? Log base 6 of 5y is the same thing as log base 6 of 5 times y. If they're being multiplied, we can rewrite it as log base 6 of 5 plus log base 6 of y. That's the product rule, okay? If we're asked to expand it, they want us to take this multiplying and make it an addition problem. Now, if they're asking us to condense it, then usually you're going to be given an addition or a subtraction problem. We're going to do addition because we're still looking at our product rule. And if we're adding things that are the exact same logs with the same bases, we're going to work backwards. If we add them, we're going to actually take our two ofs and we're going to multiply. Okay, that's our product rule. So log base 3 means our answer is going to have a log base 3. And then we're going to do 10 times x, so 10x. And that's condensing versus expanding. So when we compress a logarithmic expression using the product rule, the bases of the logarithms must be the same, okay? So those bases have to be the same, honestly, not just when you compress it, but also when you expand it, okay? So you want to make sure that the bases are the same. If you saw something like this, oops, sorry about that, okay, log base 2 of 8 plus log base 3 of y, and you're asked to compress it or to make it smaller or to simplify it, you can't, okay? There's no way to do this. You can look at it as these two things are not like terms right now. Log base 2 and log base 3 cannot be combined. There's no way to do it at this point in the chapter. Okay, so we're not going to worry about it. This is not our product rule. So let's just check for our understanding. Okay, we'll do a couple examples together. So they want us to expand this, and I see that it's 3 times a. When I'm multiplying my ofs, I can write it as an addition problem. So they have to both be log base 2. So I'm going to come here, I'm going to do log. Ooh, I don't want to do that log. I want to do that. Ooh, well, that was a mess. Let me just delete it all. I'm sure you make mistakes too, right? There we go. So I'm going to go to the log with a little b. So I'm going to have log base 2, because it has to stay the same, of 3. And I'm expanding it, so it's multiplication. I'm going to make it an addition problem. Then I'm going to do log base 2 of a, right? Because if they're multiplying, I can expand it to addition, and check-a-rooney, looking so good, okay? Next, we're going to condense this next problem. So they both have the same bases, which means they're kind of like terms. I can combine them. When I combine them, I multiply my of. So I'm technically doing a 2y times 8. Well, 2 times 8 is 16. I'm just going to tack on my y. Everything else stays the same. So it's going to be log base 5 still. And then 2 times 8 we said was 16. And then my y is going to stay right on in there. So good. Okay. Hopefully you feel good about that. Now the quotient rule works almost the exact same. If you're asked to expand it, you're going to put your numerator, okay, as the first piece. You have to keep the logs and the bases the same, and your denominator is going to be what is subtracted from it, okay? If you're asked to condense it, you need to make sure you write your fraction or your division in the correct order. So if we have log base 4 and log base 4 and they're being subtracted, I can combine them. I'm going to do x to the third over y, okay, x to the third over that y. Again, your bases must be the same. Like here, you cannot actually write that as a fraction. They're different bases. You cannot use the quotient rule to help you out here. So we're asked to expand this. It's log base b of 4 divided by c. So to expand it, who cares that there's a variable there? Let it go. If that made you anxious right then, let it go, okay? We're just asked to expand it. So that means I'm going to write it as 2 pieces. I'm going to have log base b, make sure you do lowercase, of my numerator, 4. And then I'm going to go on the outside. Minus, right, top minus the bottom, log base b, because they have to both be the same and they have to mirror this one right here. And I'm going to put a c right on in there. Oops, not there, right in here. Okay, and we'll give it a checkaroo. Good to go. And then lastly, we're going to combine these two things. So here we just have log and log. This is what we call the common log. We're going to do a whole lesson on this towards the end of next week. So don't worry about it for now. We're just going to type in the log. And then if we're subtracting, we're going to have a fraction with this log. Whoa, that's not what I want to do. we're going to type in log. They have no parentheses, so we're going to put a parentheses. There we go. Now we have to have a fraction. Our numerator is going to be our first piece, 3z, and our denominator is going to be our next piece, 8. And we'll check it. Good to go. Okay. Now the last piece is the power rule, and really that just says our of piece, if it has an exponent, that exponent can be a coefficient in front of a simplified log. Okay, the base has to be the same. This value here before the exponent was raised to it has to be the same. This will come in handy later, but mostly you will use it, you'll be given things in this form and put the number back up here and then simplify that. Okay, but either way, let's talk about expanding it. So expanding it means you have it with the exponent on the inside. You need to take it from here and move it right out front, and then you're done. The log base stays the same, the m value stays the same. Pretty straightforward. If you're given something with a coefficient in front of your log, and this is what you're going to see more often, you need to know that that 4 can be moved to be an exponent on the 2. Okay, so for example, if we look closer at that at that specific problem, right here, 4 is our coefficient. It's the exact same thing as if it was an exponent. So 2 to the 4th is 16, and we could simplify it a little bit. Okay, and then now we can actually solve this. We could say 5 to the what power equals 16. That's a really crappy number. It's not something I would expect you to be able to calculate in your head. Okay, so let's do a quick check for our understanding. They want us to expand this. I see there's an exponent in here. I'm going to bring it right out front. So it's going to become 5 log base 7, right? That has to stay the same of just my normal piece in here without the exponent, so just x. And we'll give it a check. And then we'll come down to condense this. Now, again, you're not familiar with this. This is called the natural log, okay? We are going to spend a day talking about that also, the same day that we talk about common log. We'll talk about the natural log a little bit, but you're going to let it go right now because we're just doing a couple practice problems. It's really about the properties, right? So I could take that 6, I'm going to move it to be y to the 6th power. So I keep my log the same. It's going to be a natural log. I'm going to add parentheses because Con doesn't do it this time. And then I'm going to have and I just clicked on this button right here. I'm going to have a y to the 6th power. Right? Because that 6 can be moved as an exponent, and I'm good to go. Okay? Now, here's some challenge problems that's going to have a couple things mixed together, and we'll do a couple of these, and then I want you folks to try. We'll do these too, and then I want you to go to Khan Academy, and you're actually going to do this practice here. I've also sent it to you. It is practice using the properties of logarithms. Okay? So this one's going to have a couple in it. First things first, I noticed it's division, right? So this division problem can be written as a subtraction. So anything that's an addition here, I'm thinking is a no-go. Okay, so that's not anything. That's like addition and, oh, maybe there's addition and subtraction. Because I noticed there's multiplying here. So I wish I could write on this right now. It's not letting me. That's frustrating. You know what we're going to do? We're going to go like this. And then we're going to solve it and then see if we can find something that matches. So let's go here. Okay, so here's the problem we were given. Log base b, and I noticed that it's a division problem. So I'm going to first start out by writing it as a subtraction. So I'm going to have log base b of my numerator, 2x to the 3rd. And then I'm going to minus log base b of my denominator, 5. Now this is pretty gosh darn simple, right? Okay, there's nothing more I can do here. Now here, if you saw before, I was like, oh, wait, hold on a second, okay? Because I said there couldn't be addition, but I noticed 2 is being times by x to the 3rd. That's multiplication right there. If it's being multiplied, I could write it as an addition problem. So I can actually expand this piece out some and just save this and tack it on at the end, okay? So now I'm just going to look right here. And I have log base b. And then if it's being times, I can actually write it as an addition problem. So log base b of 2 plus log base b of x to the 3rd. And then it's not going to be way the heck over there. It's going to be right down here. Minus log base b of 5. Okay. So now I see it is 3 pieces. I added these because these 2 were being multiplied. I subtracted these 2 big chunks first because that was a division. Now there is actually one more thing I can do here. This is as simple as it can get. However, we have an m, right? Some value raised to an exponent. I can take that 3 and put it right there. So this would be as expanded as it could get. So log base b of 2 plus 3 log base b of x minus log base b of 5. Let's take a look. Oh man. Log base b of 2 plus 3 times log base b of x minus log base b of 5. I think that's what we ended up having. Oops. Whew, good. Ooh, that was a tricky one. Let's take a look at this one. Okay, it looks like here they're giving us a subtraction that maybe they want us to condense because all of these look a little bit smaller. So I'll take a quick little screenshot of that and we'll give that one a go. These are a little bit more challenging than the practice you're going to see. Okay, so let's give this one a little practice-rooney, see what we can do. We'll move it over. All right, so let's take a look. First things first is I notice that it's subtraction. Okay, so I get that it's going to be a fraction at the end. Okay, and it's going to be log base 2. But I also notice that both of them have coefficients. So I should probably take care of that first. I'm going to take this 3 and I'm going to make it a power here. So I'm going to have log base 2 of x to the 3rd. I can't simplify that. Minus, instead of a 2 here, I'm going to put that on the 5. Log base 2, 5 squared. Okay, and 5 squared is 25, so I'll rewrite that next time. Now I'm subtracting things that have like bases, which means I can write it as log base 2 and then a division problem, where I do my first piece as my numerator, x to the 3rd, and my second piece as my denominator, and it's 5 squared, so I'm just going to make it 25. Then I should look and see, can I simplify this any further? Now, if this had a 5 in front, then I could simplify it, right? I could divide both parts by 5 since it's a mono over a mono. But right now, there's nothing else I can do. I'm ready to go back and check x to the 3rd over 25. So log base 2, x to the 3rd over 25. That's what I want to choose. Okay. Remember, here, if you look, it looks like they just did 3 times -2. We don't times those, right? These numbers in front are the exponents. This number is an exponent, okay? Then we're subtracting, which means you divide as that last piece. So hopefully I'm explaining it right. Yay, I am. Okay? So, like I said, you're going to be asked to do this practice right here as your other homework for Khan Academy. However, I hate to say it, I'm still not done yet. I want to hop back to my presentation so that you can preview what we're going to practice next time. Next time, we're going to be applying these properties of logarithms to actually solve. You have no solving in your homework. You can see it just says practice the properties here, and you already saw your other Khan Academy practice. But when we get together, okay, or when you log in on Monday, you're going to see that you're going to have to practice things and it's going to look like this. Okay, so right now you can write these down if you want to. We're going to do 8 problems together in the next video. All right, but I want you to see what's coming down the pipeline for you and what you're going to spend all of our next time together doing. Okay, so if you really want to, you could stop right now and do that Khan Academy practice, but I really want you to preview this. So, you are going to be asked at some point soon to solve. Okay, solve means that you're going to have a hot mess of properties and then equals something else. Now your equals could be a number, like it is here and here, or it could be equals another log. So the idea is just like a normal equation. You're going to simplify one side, simplify the other side, and then start moving things across and or rearranging it. Okay, and so we're going to do this one nice and slow. We're going to do actually all 3 of these pretty slow. So we're going to ignore this equal sign right now. Here's our wall, just like a normal equation. And I'm going to simplify it as much as I can. So I notice these are both log base 6s, which is good. It means I'm going to be able to combine them. I notice that it's an addition problem. So hopefully you're like, oh, if we're adding them, that's one of our properties. If we're adding 2 logs with the same bases, we're actually going to take our ofs and we're going to multiply them. Okay, so I'm going to take my x and I'm going to times it by my x minus 9. And then I can have them be combined into the same log with the same base. So I'm going to have log base 6 right now. And then I have x times x minus 9, which means I have x times x, which is x squared. And then x times minus 9, which is minus 9x, equals. So right now I'm going to ask you, is there anything else I can simplify here? You might be like, oh, can I put my 2 in front? Now you would be able to put the 2 in front if and only if this x squared was the only piece in here. But because it's a binomial, I can't. And again, this is subtraction. I'm not going to make it a fraction because this is in its own log. These are already combined. It just happens to be a binomial as our of piece. So there's nothing else I can simplify over here. I'm going to just bring down my 2. There's nothing I can simplify here either. So this is where we have to go back a couple beats and we're going to be at evaluating again, okay? So I've simplified it so that I have a log on one side and something on the other side. I need to change it to exponential form. I need to get them to be the same base, and then I can set it as exponent is equal to exponent. And that's why we're doing these all together, okay? So this is a 6, so I technically have 6 to the second power equals this. So 6 to the second power equals my of piece, x squared minus 9x. Well, we can solve this. 6 squared is the same thing as 36. And now I'm going to move this 36 over here and set it equal to 0 because I'm going to have x squared minus 9x. I said I was going to subtract 36 to bring it over. Minus 36 equals 0. Hopefully you're realizing, oh, great, Mrs. White, I can solve that, which is actually a good thing, but it is a quadratic, right? Everything is tying together at this point in the year. This is why we learn math in the order we do, so that when we get to the harder problems, we can actually solve them. If we never did quadratics this year, you'd never be able to tackle these logarithms. So anyways, in order to solve this, like I said, it's a quadratic. We're going to check for factoring. So what multiplies to be a times c, so it multiplies to be negative 36, and adds to be negative 9. If it multiplies to be a negative, one's negative and one's positive. And if the sum is negative, the bigger number must be the negative number. So hopefully you're thinking negative 12 and positive 3. They add to be negative 9 and they multiply to be negative 36. Because we have a leading coefficient of 1, I end up with my factored form being x minus 12 and x plus 3. Which means my two answers are x equals 12 and x equals negative 3. Now, just like before, okay, I have to take these answers, I have to plug them in and make sure that things work, okay? Because there is some issues that I could have. If you remember, and we go back, I don't think I have it on one of these previous ones. I don't, but if we go back into this Khan Academy practice, it tells us something about our m and our n, right? It said that our m and n values must both be greater than, okay, 0. So they have to be positive right here, okay? M and n must be positive. So if I come over here and I start thinking of these values, that means when I plug in this 12 here and here, I must have a value, an of piece that's positive. So if I put a 12 here, I have log base 6 of 12, that's a positive, I'm good to go. If I take 12 and put it in here, 12 minus 9 is 3, that's positive, I'm good to go. However, if I take this negative 3 and plug it here, I have an of piece now that is negative, and you cannot have an of piece that's negative. If I took this negative 3 and put it here, I'm going to get a negative 12. That also isn't going to work. So this answer does not work. The only solution we have is 12. Now, there will be times where both of them work, okay, where both of them are going to work perfectly and you're going to have two solutions. But you have to check and make sure that when you plug it in, your of pieces are both positive, okay? Write that down, star it. Both of pieces should be positive. Okie dokes. So this is like a pretty hard chunk. Like I said, this is going to be exactly what you do next time. We're going to review it a little bit and then you're just going to practice it like crazy. Okay. So here's another solving problem. It has an equal sign. I'm going to simplify over here. I'm going to simplify over here and then I'm going to rewrite it. Okay. This one actually is going to be awesome because there's a shortcut to it. So anyways, I'm going to ask you, can I simplify something over here? And I'm lingering because there's something you can do. We can take this 2 and make it a exponent on our x. So this is the same thing as log base 7 of x squared. Okay? Perfect. Can't do anything else with that. Going to leave it. Over here, I notice these are both log base 7, and that this is a log base 7, which is letting me know this is going to simplify nicely eventually. But these two pieces are being added. If we have the same bases and they're being added, we can take our of chunks and we can multiply them. So this becomes log base 7 of 27 times 3. And 27 times 3 is going to be 81. Okay? So I technically could rewrite this in exponential form, but there's even a cooler property that we haven't really covered yet. And it's kind of just like what we had when we were doing square roots. It's kind of like what we do with exponents. If you have the same log with base and log with base, and that's the only thing you have on both sides, your log with that same base cancels. And you're just left with x squared equals 81. And luckily, even though this is a quadratic, right, I'm going to square root, because I don't have to do the extra work. It's just a little mono here. And the square root of 81 gives me plus or minus, you could say 9, but I know I'm not going to be able to put a minus 9 here because then I'm going to have an of piece that's negative. Okay, so my answer is going to be x equals 9. And 9 will work because when I plug it in right there, boom, it's going to be perfect. Okay, and I can double check that that answer works. Let's take a look at this last one right now. Okay, I'm going to draw my wall. I realize I'm solving. I'm going to simplify, and then rewrite it in exponential form because there's no other logs over here, so that's going to be my strategy. No coefficient, so I don't have to worry about putting any exponents. I notice they're both log base 6, so I can put them together. It's an addition problem, so I'm going to multiply both of my of pieces. So I'm going to do x times x plus 5, which means I'm going to distribute it to both pieces. So I end up with log base 6 of x times x squared, x times 5 plus 5x equals 2. Now, there's nothing else I can do here. This is a little binomial. There's nothing else I can simplify there, okay? So because there's only a log on one side, I can't cancel it out like I did here. I have to put it in exponential form. So I'm going to do 6 squared equals this. 6 squared equals x squared plus 5x. 6 squared is the same thing as 36. So I'm going to minus 36 over here. And hopefully right now you're like, great, Mrs. White, this is so exciting. Okay, I see I have a quadratic again. So I'm going to check for factoring. What multiplies to be negative 36, right? A times C, and adds to be 5. So 36, if it multiplies to be a negative, one has to be negative, one has to be positive. If it adds to be positive, the positive has to be greater. What two numbers multiply to be negative 36 but add to be 5? So 36, 9, and 3. 9 and 4. 9 and 4. Yes, not 9 and 3. Yay. Oh my gosh, I was like nervous for a second there. 9 and 4. Okay. So those multiply to be this. They add to be this. My A value is 1, so I can put it right in factored form. And remember, at this point, it equals 0, right? Because I'm solving. I end up with x minus 4. So my solution is going to be that x equals 4. And I have x plus 9. If I set that equal to 0, I'd have a minus 9. I'm going to look back up here. If I have a 4, it will work. It will work because they'll both be positive. If I have a negative 9, it will not work here, and it will not work here. So negative 9 is not a solution that will work. 4 is. And we can double check that. Yay! So these are not any of the work I'm expecting you to do. You're going to go practice your properties. You're going to practice evaluating, if you haven't already, on Khan Academy, just those 2 Khan Academy skills, knowing that this right here is exactly what we're going to be working on, practicing all day on Monday, okay? Or whenever it is that you choose to watch the video. I'm going to do 8 examples together, and then you folks are going to have a maze to work on, and you'll have to do, I think it's 13 problems you're going to end up having to do on the maze. Not to make you anxious about it, but just so you can kind of plan ahead. I want you folks to be practicing, okay? So for now, we're building up to this. Work on those skills. Work on making sure you can identify your properties nice and quick and easy. And thank you for hanging on this whole time for our really long video today. We're getting there, folks. We really are getting there. You're looking at only 1, 2, 3 weeks left of school after today, okay? okay? So just keep working, keep asking questions, keep your head up. We're almost there, folks. I miss you, and I hope you're doing well. Bye.